Imagine a world just 35 light-years from Earth, circling a faint red dwarf, L98 to 59F. No telescope has ever caught it crossing in front of its star. We inferred its presence from tiny heartbeat-like wobbles in the star's motion. Its minimum mass is 2.8 times Earth's, its year lasts 23.1 days, and it orbits at roughly 0.105 astronomical units. Most importantly, it sits within its star's habitable zone. The discovery was announced in 2025, and the planet has since been added to the official catalogues. The stage for this story is the constellation Volans, where L9859, a cool M3V red dwarf, resides. The system burst onto the scene in 2019 thanks to TESS. 3 small transiting planets were confirmed and labeled B, C, and D. In 2021, ground-based spectrographs revealed one more planet, E, and hinted that something else lurked farther out. That missing piece was confirmed in 2025 as F, giving the system a 5-planet architecture. Scorching inner worlds inside, then E with a 12.8-day year, and farther out F with a 23-day year along the temperate edge. With its proximity and diversity, L9859 joined the league of TRAPPIST-1-style natural laboratories. So how do we find a planet that doesn't transit? By watching the star wobble. As a planet orbits, it tugs its host star back and forth at imperceptibly small speeds. Spectrographs like HARPS and ESPRESSO can measure Doppler shifts in the star's spectral lines down to centimeters per second, tracing out a sign-like signal. For L9859F, a long baseline of TESS monitoring combined with archival HARPS ESPRESSO data made the case clear. A 23-day period, a small but consistent signal pointing to a non-transiting super-Earth. That painstaking work pinned down the planet's minimum mass and orbit. Here's the crucial part. Does habitable zone mean actually habitable? Not necessarily. The habitable zone is the range of stellar energy that could allow liquid water on a planet's surface. L9859F receives roughly Earth-like irradiation, making it an intriguing entry on the list of temperate worlds. But without a transit, we don't know its radius. That means density and surface conditions remain unknown. Is it a water-rich world wrapped in a thick atmosphere, or a rockier planet with a thinner sky? Both are plausible. What makes a world habitable is not just the starlight it gets, but the full blend of atmosphere, pressure, albedo, magnetic field, and the star's activity history. With red dwarfs, the plot thickens. The good news, M-dwarfs live a very long time, great for biology. The tough news, many are feisty in youth, flaring and blasting their planets with high-energy photons and stellar winds that can erode atmospheres. That's why a nearby multi-planet system like L9859 is gold for science. As we nail down the masses and radii of the inner transiting worlds B, C, D, we can compare them to the more temperate E and F to study inside-out evolution, atmospheric escape, volcanism, and formation history under the same star. A family of planets around one sun gives us a built-in set of experiments. No transit doesn't mean no atmosphere, but it does make things harder. JWST's classic transit spectroscopy is off the table for F because it never crosses the stellar disk from our line of sight. Still, paths remain. First, longer, ultra-precise radial-velocity campaigns can better constrain the orbital inclination, and thus the true mass. Second, upcoming giant telescopes, like the ELT, can improve stellar activity modeling to tease out low-amplitude signals and may enable indirect probes such as phase curves or thermal emission hints. Third, if there are additional faint signals in the system, dynamical stability studies, TTVs, eccentricity maps can sharpen the architecture. All of this moves us step by step toward answering, what kind of place is this? L9859F's scientific value isn't just that it's nearby and temperate, but that we can interpret it in the context of its siblings. The inner planets are likely more sun-drenched and more vulnerable to atmospheric escape. E and F sit in a gentler flux regime. If F turns out to have low density, a high water content scenario gains traction. If it's dense, a metal-rich, rocky super-Earth picture emerges. Either way, read alongside its sister worlds formed in the same disk, we can test ideas about inside-out material sorting, water delivery, and late-stage bombardment. That's why catalogues moved quickly to log L98-59F. For observers, it screams follow-up target. Let's give the numbers some intuition. 23 days is about 1/16th of an Earth year. The semi-major axis is 0.15 AU, roughly a tenth of the Earth-Sun distance. If it's that close, why isn't it roasting? Because the star is small and cool, a dimmer, redder cousin of the Sun. To receive similar energy, a planet must orbit closer in. This is the trade-off we often see in M-dwarf systems, a close-in temperate zone, but with potential challenges like tidal locking and stellar activity. For L98-59F, it's too early to say how decisive those risks are, but that's where science thrives. Measure, model, compare, measure again. There's still a big blurring unknown, the radius. If it transited, a single light curve would give us radius and density, bringing the rocky or water-rich question into sharp focus. Non-transiting status makes characterization tougher, not impossible. Continued RV monitoring, better stellar noise models, and, in the long run, precision astrometry to pin down inclination could unlock the mass puzzle. Later, advances in high-contrast techniques might enable phase curve-like measurements. It's a long game, because it has to be. But for a multi-planet system practically in our cosmic neighborhood, the effort is well worth it. Now zoom back to the system as a whole. From 2019 to 2025, one space telescope, TESS, and two ground instruments, HARPS, ESPRESSO, worked in concert, first flagging the hot inner worlds, then confirming the milder outer ones. This is modern exoplanet hunting in a nutshell: wide-field space surveys, then precise ground-based confirmation and characterization. L98-59F's story is a textbook example of that choreography. Finally, the big question: could there be life? The honest scientific answer? We don't know. We do know the stellar energy it receives is compatible with liquid water, that its minimum mass places it in the super-Earth class, and that its surface and atmosphere remain hidden, for now. But a few years ago, we weren't even sure it existed, and today we're discussing it. At this pace, tomorrow we may catch hints of its air. The day after, we might infer the balance between surface and sky. That's why L98-59F is poised to become a standout on the shortlist of nearby temperate worlds. If this journey excited you, don't forget to subscribe, hit like, and tell me in the comments how you imagine L98-59F, rocky continents under thin clouds, or a deep ocean beneath a hazy, thick atmosphere. Science rewards good questions, and the best part is this: with every new question we ask together, we get a little closer to the answer.